After studying this module, you shall be able to know in brief about chemical bonding, learn about valence bond theory, learn about molecular orbital theory, or learn about symmetry of atomic orbitals. Also, you will learn the overlapping of atomic orbitals. You will also know the conditions for overlapping of atomic orbital and also know what is hybridization, why it is needed in chemical bonding. You will learn the scheme of hybridization of atomic orbitals, detailed procedure for finding hybrid orbitals for ABN type of molecule will also be taken care. Also, you will learn the hybridization in CH4 molecules. Group theory and molecular symmetry can be applied to the understanding of atomic structure, bonding in molecules, hybridization, electronic spectra, reaction mechanism, etc. Modern views of atomic structures are largely based on the application of wave mechanics to atomic structure. Studies involving wave mechanics have answered long-standing questions to many problems associated with chemical bonding. Thus, ultimate description of chemical bond lies in quantum mechanics and solutions of the Schrödinger wave equation. Chemical bonding is very well described by two well-known theories: valence bond theory (VBT) of Lewis structure, second molecular orbital theory (MOT). These theories are well defined and well described in each and every book on chemical bonding. In this model, I will not say much in detail about these theories. A brief introduction of these will be made here. Now, the concept of hybridizations gives the idea of involvement of the atomic orbitals in chemical bonding. Hybridization can explain the equivalence of bonds involved in bonding. Now, in theories of chemical bondage, these two common theories, that is the valence bond theories and MO theories. Let us take one by one in very brief. Valence bond theory, it is the simplest and oldest theory, and this theory was developed by Hitler in London. Valence bond theory is an extension of Lewis dot idea of formation of a bond. The valence bond theory is a quantum mechanical model, describes distribution of electrons between the bonds and was developed from Lewis and VS-EPR theories. This theory provides localized view of bonding. Valence bond theory cannot explain the exact bonding in polyatomic molecules. Valence bond theory can explain many of the properties of the molecules. Valence bond theory takes into account of the specific and localized atomic orbital on each and every atoms, which undergo interaction and overlap with each other to form a chemical bond. According to VBT, these interactions have localized effects, but these can be extended to polyatomic molecules if due consideration of geometrical orientation of various atoms in molecules is taken care of, as mentioned is in VS-EPR theory. Properly oriented atomic orbitals and described molecular shape presented many difficulties in explaining the bond length, bond strength, bond angles in polyatomic molecule. To overcome such difficulty, Linus Pauling proposed the idea of hybridization involving atomic orbitals to give equivalent hybrid orbitals equal in number to the number of atomic orbitals involved in hybridization. Now, no attempt will be made to discuss this VBT in detail. Valence bond theory generally describes the formation of CH4, that is tetrahedral molecule, in terms of sp3 type of hybridization. But there are other possible combination of atomic orbitals which have the same tetrahedral geometry. By using the technique of molecular symmetry and group theory, it is possible to find all sets of possible combination of atomic orbitals which can lead to same geometry of the molecule, that is the tetrahedral geometry in case of CH4. Now, before going into further, let us see the shape of the common atomic orbitals which will come across during this module. And all this type of shape, these are well known to you, and these are given in, that is, we have s, p orbitals, d orbitals, etc., and also we have the 7f orbitals also as shown into the figures. Now, these are the common shapes which are well known to you, and these will be needed in further this model. Now, shaded area into this f orbitals shows the positive sign of the wave function for this. Now, before going further, let us discuss some symmetry characteristics of these atomic orbital. An s orbital is spherical in nature, possesses an infinite number of C infinity axes, that is, n varies from 1 to infinity. It has infinite number of planes of symmetry and center of inversion. A sphere has highest possible symmetry as shown in this over here in this module I am showing. This is sphere, all I am having x, y, z axis into this, and this module has all possible infinity axis. You can pass any axis through any point, it is there. It has number of symmetry planes into this. So, this sphere is a module, or you can say is an object which has infinite number of symmetry elements present into this molecule. In p orbitals, the lobes have different signs for wave functions. These cannot be interchanged by any symmetry operations. These are symmetrically non-equivalent. It has no plane perpendicular to long axis of the orbital. However, it has infinite number of planes that pass through both the lobes and contain the long orbital axis. The long axis, that is the axis along the orbital. In fact, it is C infinity as shown over here. Now, suppose I take this px axis like this is my y axis and this is z axis, and this lobe and this lobe, there it is the positive lobe over here, this is the negative lobe over here, and there is an axis which passes through this. It is C infinity axis which passes over through this. So, in this px molecule we are having this type of symmetry, that is, this is a C infinity axis which passes through this, both the positive lobes and negative lobes. Like this we can describe other p axis, py axis and pz axis. Now, similarly we can have d orbitals, dxy, dxz and dyz orbitals. Now, in this dxy, dxz and dyz orbital, there are pairs of positive and negative lobes which can be interchanged by the inversion symmetry, that is, it has center of symmetry. It has three mutual perpendicular C2 axes, and these mutually perpendicular mirror plane also, and these symmetry elements are shown into the figure, that is, all the C2 axes are shown. Now, in dz square orbital, it has again two positive lobes along the long axis and a negative torus or a ring around its middle portion. It has center of symmetry, Second, a sigma perpendicular to C infinity. And third, infinite number of C2 perpendicular to C infinity axis which pass through the center of orbital. It has S infinity axis also. So, with these small symmetry properties, this whole dz square orbital is shown in the figures. Now, for hybridization or the sum of the overlapping of atomic orbitals, that is for hybridization, the overlapping of atomic orbitals, we are having some of the common overlappings, that is which gives us the bonding, anti-bonding type of and non-bonding type of atomic orbitals. If the px over atomic orbitals, they go for end-on overlapping, sigma bond is formed. If there is a sidewise overlapping, we get pi type of orbitaling. All these various types of overlapping with s is equal to 0, s is greater than 0 and s is less than 0 are shown in this diagram over here. Now, where s is less than 0 and s is greater than 0 signifies negative and positive overlapping respectively. There is another type of bonding that can occur between d orbitals. Taking z axis as the internuclear axis, pair of dx square minus y square or dxy orbitals on adjacent atoms can interact with each other in such a way that all the four lobes of each d orbital interact simultaneously, giving thereby delta bonding. If overlap integral s is greater than 0, then sigma bonding orbital is formed, and if s is less than 0, sigma anti-bonding orbital is formed. Now, let us take second theory, that is molecular orbital theory for chemical bonding in brief. In valence bond theory is simple and oldest theory for chemical bonding, yet cannot explain many of the bonding in polyatomic molecules. It cannot explain the paramagnetic character of oxygen molecule. Valence bond theory has many more limitations. Valence bond theory takes the localized view of the bonds. Molecular orbital theory takes into account of the overlapping of atomic orbitals and delocalization of electron density throughout the whole molecule. Schrödinger wave equation can be used to describe the behavior of electrons in molecules, and wave equation can be solved only by means of approximation techniques. Molecular orbital theory always allows the filling of the electron in molecular orbital. Each is associated with two or more nuclei, similar in many ways to atomic orbitals. Molecular orbital theory is more popular and simpler. Atomic orbital at different atoms are combined to give molecular orbitals belonging to the whole molecule. There are two methods for obtaining wave function which describes the whole molecular orbitals. Linear combination of atomic orbitals, that is LCAO method, united atom method. Now, united atom method will not be discussed here. A very brief view about LCAO method for formation of molecular orbital will be discussed. Conditions for linear combination of atomic orbitals. These are very important. The atomic orbitals involved in the process must be nearly of the same energy. The overlap between two atomic orbitals should be maximum as far as possible. That is, the overlap integral s must have the positive value, s is greater than 0. Third point, The symmetry of atomic orbitals involved in overlapping with respect to internuclear axis should be same. This is very important point. Fourth point, the molecular orbital can be bonding, that is s greater than 0, anti-bonding, s is less than 0, or non-bonding, that is where s is equal to 0. Fifth point, total number of molecular orbitals will be equal to the sum of total number of atomic orbitals used in the process. Sixth one, energies of combining atomic orbitals should not differ to a greater extent. Let us take the case of molecular hydrogen H2. Two hydrogens are labeled as HA and HB, which have 1s atomic orbital of lowest energy available for linear combination. Each of these 1s atomic orbital for hydrogen atom A and B can be represented by wave function phi A and phi B respectively. Each molecular orbital can be represented by a wave function which is suitable for combination of phi A and phi B. In case of hydrogen, phi A and phi B are identical. Each atomic orbital contributes equally to the molecular orbital. Two molecular orbitals which are obtained by LCOA method can be written as number 1, psi AB is equal to capital N within bracket phi A plus phi B obtained by constructive overlapping of two wave function, that is bonding orbital. Second, we have psi star AB N star within bracket phi A minus phi B obtained by destructive overlap of phi A and phi B. Here N and N star are known as the normalized constant, and these normalize the psi AB, psi star AB wave function. The values of these normalized constants are given as N is equal to 1 upon under root 2 into 1 plus S, N star is equal to 1 upon under root 2 1 minus S, where S is called as Slater overlap integral, given as S is summation phi A phi B dt, where dt denotes the integration is performed over all coordinates of space, that is dt is dx dy zz. S is a measure of the extent to which the two wave function add constructively. Its value is generally low and is neglected during normalization process. The value of n is equal to n star is equal to 1 by under root 2. Therefore, S for hydrogen can be calculated or approximated. It is only desired for our purpose to know whether S is greater than 0, S is less than 0, or S is equal to 0. If S is greater than 0, overlap results in bonding molecular orbital, that is, there is a constructive addition of two wave functions and electron density is built up between two hydrogens nuclei. If S is less than 0, overlap results in anti-bonding molecular orbitals with much less electron density between two nuclei. That is, there is a destructive addition of two wave functions. If S is equal to 0, overlaps result in non-bonding molecular orbitals in which distribution of electron density is nearly the same as that described by atomic orbitals of two hydrogen atom. Thus, the two normalized molecular orbitals psi AB, that is sigma 1s, psi AB star, that is sigma 1s stars, are given by the expression, that is psi 1s is equal to psi AB is equal to 1 upon under root 2 within bracket phi A plus phi B, This is a centrosymmetric. Sigma 1s star is equal to psi star AB is equal to 1 upon under root 2 phi A plus phi B, non-centrosymmetric. This is the figure which shows the formation of this. Now, the figure further shows how the 1s and 1s overlap each other to give centrosymmetric bonding MO sigma 1s, that is psi AB, and then there is a destructive addition of 1s and 1s to give non-symmetric psi B, where in this non-symmetric we are having a node in between. These are shown into the molecular symmetry and group theory plays vital role in describing symmetry properties of MO and their construction. Before discussing the hybridization, that is, we will now discuss hybridization. Before discussing the hybridization scheme in molecule, let us first take the transformation properties of atomic orbitals. The Schrödinger's wave equation can be solved completely for hydrogen atoms and for related ions which have electrons in them, such as helium positive, lithium 2 positive. For other polyelectronic spaces, only approximate solution can be obtained. Schrödinger's wave equation for polyelectronic system can be easily solved using polar coordinate system instead of Cartesian coordinate system. A relation between Cartesian coordinates, polar coordinate system can be explained as shown into the, and these relations are given as x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, z is equal to r cos theta, where x, y, z are the Cartesian coordinates and polar coordinates are r, phi and theta of a point, which are shown in figure. The Schrödinger's wave equation involving polar coordinate system can be written as shown in equation 1. Psi is equal to r within r, theta within bracket theta, phi within bracket phi, where r is a radial function that depends upon the radial distance r from the nucleus, which depends upon n and l quantum numbers only. Theta into theta within bracket theta is a function of theta which depends upon L and M quantum number. Phi is a function of phi which depends only on quantum number M. Can be rewritten as psi is equal to capital R within bracket R NL and capital A ML. It means this splits the wave function in two parts, and these can be solved separately. NL has no physical significance. The AML depends only on the direction and does not depend upon N and L. Only this angular part of the wave function can change under symmetry operation of the point group. So, only this angular wave functions will be considered for symmetry point of view. The angular function AML is known as spherical harmonic. For various atomic orbitals, these AML functions are listed in table, that is S is a totally symmetrical, Px sin theta cos phi, Py sin theta sin phi, Pz is cos theta, dz square is 3 cos square theta minus 1, dx square minus y square is sin square theta cos 2 phi. Like this, we are having dyz is sin theta cos theta sin phi. The subscript to these atomic orbital symbols are directly related to the angular function. For example, function sin theta cos phi for px orbital is related as x is equal to r sin theta cos phi. R does not change by any symmetry operation of the point group. Therefore, sin theta cos phi will transform in the same way as Px or x transforms under symmetry operation of the point group. Similarly, angular function sin theta sin phi and cos theta will transform as Py or y, Pz or z respectively. Now, the transformation properties of some of the atomic orbitals are summarized in the table, that is S is equal to x square plus y square plus z square, Px will transform as x, Py will transform as y, Pz as z, dx square minus y as x square minus y square, and so on, dxz as dyz. Thus, we can easily determine the transformation properties of any orbitals on central atom, and just by looking the corresponding subscript x, y, z, x square, y square, z square, x, y, x, z, y, z, etc. in the proper column, so right side of the corrected table of that point group. The s orbital is always symmetrical and transforms according to the totally symmetric representation. Discussion of symmetry properties of atomic orbital so far has taken into account the fact that we are dealing with one electron orbital of the hydrogen or hydrogen-like atom or ions. As mentioned earlier, the treatment can be extended to polyelectronic species. The wave function for this system can be written as the product of one electron wave functions. Now, let us take symmetry of atomic orbitals for hydrogens. We generally deal with a molecule in which the central atom is A. The atom A is surrounded by a set of other atoms which are bonded to A. To know which atomic orbitals of A can be used to produce symmetric hybrid orbitals about a bond axis, it is necessary to know to which irreducible representation of the molecule's point group the atomic orbitals of the central atom belong. That is, for which irreducible representation of the molecule's point group the atomic orbital on the central atom form a basis for representation. This can be directly read from the corrected table of the point group. Gives the geometry or shapes of hybridization scheme of the various molecules. This table shows various general geometrical shapes possible. That is, what is the coordination number, what is the geometry, and what is the possible hybridization, and what is the shape. Now, for example, when coordination number is 2, it can be either linear or angular, and the hybridization can be SP, dp for linear, angular ds or p2 or d2, and the shapes are shown as BAB or BAB angular. Similarly, for 3 coordination number, it is a trigonal planar, and the shape can be SP2, DP2, DS2, D3, and the shapes can be trigonal planar. Then unsymmetrical planar trigonal pyramidal molecule we are having, as the shape is shown over here, and the hybridization is for unsymmetrical planar molecule is DSP, and for trigonal pyramidal it is the P3 or D2P. And for 4 coordination we can have tetrahedral, tetragonal pyramidal, irregular tetrahedron, and tetragonal planar, and various possible hybridizations are sp3 sd3, d4, then d2sp, dp3, d3p, and so on, and the shape are shown as tetrahedral, and then we are t-type, and then we have square planar structure. Similarly, we have the various possible geometry for 5 coordination geometry, and these are trigonal bipyramidal, tetragonal pyramidal, pentagonal planar, and pentagonal pyramidal, and also the various types of hybridization is also shown over here, and the possible shape, that is the trigonal bipyramid and pentagonal pyramid is also shown. Similarly, for coordination number 6, we can have octahedron, trigonal prism, trigonal antiprism, and mixed geometry, and various types of hybridizations are also shown over here. Now, after saying about the type of possible geometry, let us go for the hybridization of atomic orbitals. Hybridization is a concept that allows us to account for certain key structural issues that are not easily accounted for in any other bonding theories. The concept involves the cross breeding of atomic orbitals to create new orbitals, hence the use of the term hybrid. Linus Pauling first developed the hybridization theory in order to explain the structure of methane, that is CH4. The concept was developed for each such simple chemical system, but the approach was later applied more widely and totally. It is considered an effective concept of rationalizing the structure of inorganic and organic molecules. Orbitals are model representation of the behavior of the electrons within the molecule. For simple molecules like hydrogen, the hybridization is simple and involves direct overlaps of atomic orbitals on two hydrogen atoms. In heavier atoms, which use atomic orbitals of the type 2s and 2p orbitals, hybrid orbitals are assumed to be mixture of these atomic orbitals, superimposed on each other in various proportion. It provides a quantum mechanical insight to Lewis structure. Hybridization theory finds its use mainly in organic chemistry. The different types of hybrid orbitals, which have different orientation in space, account for the different geometries of the organic compound. The scheme of sp3 hybridization can be depicted as, that is, let us take 2s orbital of carbon and 2p orbitals of carbon. 2s is completely filled up, 2p is 2 electrons in 1 and 1. Hybridization of atomic orbitals, we need 4 equivalent hybrid orbitals, and by doing this we get these 4 equivalent hybridization as shown to the figure. We use 1s orbital and 3p orbitals, and after hybridization we get 4 equivalent hybrid orbitals, and with these 4 equivalent hybrid orbitals there are attached 4 hydrogens. It means each of the CH bond in CH4 is chemically equivalent. Now let us take hybrid orbitals for sigma bonding system ABN type of molecule. A sigma bond is symmetrical about the bond axis. Here we will find which atomic orbitals of A can be combined to form equivalent hybrid orbitals which are symmetric about AB bond axis in ABN molecule. To explain this, let us again take TD point group molecule CH4. Since there are 4 CH bonds, we require 4 hybrid orbital center on carbon atom, which can combine with 4 hydrogens. We know all the 4 CH bonds are equivalent in all respects. We need 4 hybrid orbitals which are identical in all respects and directed along the 4 corners of a tetrahedron. These hybrids will be LCAO of carbon atom. These hybrid orbitals will form the basis of some irreducible representation of the molecule point group. This set of hybrid orbitals forms the basis for reducible representation that is tau hybrid. The reducible representation so obtained can be reduced. How to find tau hybrid? For this, let us take CH4 molecules, which is described in a cube, and label each hybrid orbitals, that is each CH bond, by a vector R. That is, I take this a CH4 molecule like this, and each of the bonds, say carbon-hydrogen bond, there are 4 carbon-hydrogen bonds, and I label them as R1, R2, R3 and R4. These are shown into the model over here, and these hybrid orbitals, and we will now follow a procedure as described in earlier modules for finding reducible representation by taking these bond vectors as the basis for representation. And we know the general thing, the vectors which are shifted by symmetry operation of the point group contribute chi is equal to 0 to tau hybrid. The vectors which are not shifted contribute chi is equal to +1 to tau hybrid, and the vectors which are not shifted but only the direction of which are reversed contribute chi is equal to -1 to tau hybrid. The symmetry operation belonging to the same class of the point group have same effect on the vectors, and thus each contribute same character to tau hybrid. The results of all these are shown in the table. That is, first row shows the vectors unshifted, then chi contributed, multiplication factor, and then tau hybrid. Unshifted vector for E it is 4, for C3 1, for C2 it is 0, for S4 is equal to 0, for sigma D it is 2. That is, if I take this, and for E all the 4 vectors are not shifted. For C3, if I give this rotation, only this bond vector will not shift. For C2, if I take like this, that is, I rotate it like this, all vectors are shifted. For sigma D, if I take like this bond vector and this bond vector will not shift, that is, only 2 bond vectors are not shifted. So we get tau reducible as 41002, and this tau can be reduced as A1 and plus T2. This equation tells that there are 4 atomic orbitals of carbon atoms which are combined to give the set of 4 equivalent hybrid orbitals, and they are chosen in such a manner that each hybrid orbital has a contribution from one atomic orbital which belongs to A1 representation, that is, AS has A1 symmetry, and 3 atomic orbitals which belong to triply degenerate, that is T2 representation. Now let us look about the symmetry species of atomic orbitals of carbon atom. For this, I have to look up the character table of TD point group, that is, which is given, and here we will note down find the A1, it is a totally symmetrical, and T2 has XYZ or XYYZ XZ as the basis. The results for various atomic orbitals of carbon together with their symmetry is summarized as A1, it is the s orbital, T2, it can be Px, Py, Pz, or dxy, dxz, dyz. Under E, we are having dz square, dx square minus y square. It means that we have to take one atomic orbital of carbon atom which belongs to A1, irreducible representation, and 3 atomic orbitals of carbon which belong to T2, irreducible representation. E part we will not take up because it is not the part of irreducible representation. The possible combination of atomic orbitals to give 4 equivalent hybrid orbitals are S from A1 symmetry plus Px, Py, Pz from T2 symmetry, that is sp3, or S from A1 symmetry plus dxy, dxz, dyz from A to symmetry. The possible combination of suitable atomic orbitals are sp3 or sd3. According to symmetry concentration, both set sp3 and sd3 are equally possible set of hybrid orbital. Symmetry arguments cannot tell further whether it is sp3 or sd3. Our chemical intuition tells that for such problems, the possible solution would be a linear combination of these two, that is psi c is equal to A times sp3 plus B times sd3, where psi c is the carbon atom hybrid orbitals. Values of A and B can be obtained by quantum mechanical calculation. Our chemical arguments point towards the fact that in carbon, s and p orbitals have energy much near to each other, and this can overlap easily, while d orbitals are of high energy have little chances for overlap. Thus, psi c is approximately a sp3. However, for species of the type chromate ion or molybdenate ion, contribution from sd3 is more and hence cannot neglected. It is to be noted further that dz square and dx square minus y square orbital on carbon atom are not involved in formation of the four equivalent hybrid orbitals. The dz square and dx square minus y square orbitals transform as E in TD point group, but set of four hybrid orbitals in carbon atom form the basis for A1 and T2 representation only. Hence, no E representation is taken care into this. Thus, in this module, we have discussed in brief about chemical bondings, that is valence bond theory in very brief, molecular orbital theory in very brief. We have discussed the symmetry of atomic orbitals, overlapping of atomic orbitals, and the conditions for overlapping of atomic orbitals have been discussed. What is hybridization, why it is needed in chemical bonding has also been explained in very brief. Symmetry of atomic orbitals in light of overlapping has been explained. Scheme of hybridization of atomic orbitals from symmetry point of view has been explained. Detailed procedure for finding hybrid orbital for ABN type molecule, that is particularly methane CH4, has been explained in detail.